Okay, this is Dr. Hold. I want to go over this problem here. Here I have three masses, a 12 kilogram, a 40 kilogram, and a 16 kilogram. They're attached by two cables. One has a 1 kilogram mass coming between the 12 and the 40 kilogram object. Another one has a mass of 1 kilogram between the 40 and 16. Alright, what we can do here is we can look at this whole thing as a one entire system to start out with. And we can find out what the total mass is. And what the total mass of that would be, if we add that together, would be 70 kilograms. Alright, so now I'll just go ahead and erase what I did, the circle here. Okay, so now we can go back to Newton's second law and say the summation of forces in a certain direction, and we'll let this be the x direction going this way here. X direction must equal to the mass of the objects times the acceleration in that direction. So when we sum our forces, the only force I have is 140 newtons. So I can say 140 newtons is equal to 70 kilograms times the acceleration in the x direction. And we will get the acceleration in the x direction here to be nothing more than 2 meters per second squared. Now let's just find some points here. Let's say we want to find out what the force is going to be here, what the force is going to be here. This color is different colors. What the force is going to be here, and we'll say what the force is going to be at these locations here. Alright, so if I'm going to do the force here, what you need to do that is draw yourself a good free body diagram. I'll come down here, and I'm going to go ahead and show the all the forces here. So if I did that, I'd have 12 times 9.8 coming down, like this, and like this. And I'm not going to run the calculation. I'm just going to make it as, I'm just going to share. I'll just make it as 12 times 9.8. So my force of gravity coming down would equal to 12 times 9.8. My normal force coming back up would equal to the same thing, 12 times 9.8. Now if there's no friction, which there's no friction in this problem, we really don't necessarily have to worry about the normal force. Alright, so now I'm going to apply the force going to this direction here. I have no force going back to the left, so we can call that the force. And I'm going to call this, let's call this C1, cable 1. That's the force that C1 is going to place on the 12. So right now I do not know what that is, but all I have to do is say the summation in forces in the x direction must equal to the mass times the acceleration. So I can say the force that cable 1 applies to the 12 kilogram object must equal to the mass of this object, which is 12, times the acceleration that we got up here of our system is 2. And when I do that, that will give me 24 newtons. So we know right now, and I'll do that in blue. Actually, I'll do it in red because we're using that color. This force at this point would be 24 newtons. Okay, so now if I want to find out what's taking place here, say we want to find out what's on the blue. Well, the easiest way to do the blue is to draw a free body diagram of this cable here. I'll come down here and do this one. It's sitting here. I'm not going to include the vertical forces. We'll just include the horizontal. So what I would have would be a force coming, oops, do it with a vector. Be a force coming back. A force going back this way. Now in this problem we found 24 newtons, that the force that cable 1, this force here, the cable 1 was pulling on 12. So we must say that the force that 12 is pulling on C1 must also equal to 24 newtons. Because there's a force pair. There's a force pair right there. Let's straighten this vector up. It doesn't look right. Okay, so then we'll say, call this F, I don't know, call it the F that 40 is placing on C1. Okay. Now we'll do the same thing. When I sum my forces in the x direction, it must equal to the mass of that object times the acceleration in the x direction. When we do that, we'll get minus 24 plus the force that 40 is applying onto C1 is equal to the mass, the 1 times acceleration, and we said the acceleration was 2. When we solve for that, we will find that the force that the 40 kilogram object is doing on C1 is going to equal to 24 plus 2, that's going to be 26 newtons. And we'll do that in blue. Okay, so now let's do it green. To do green, the easiest way to do it is just do a free body diagram right here of this object, of the 40 kilogram object. So when I do that, I will draw it, and I'll go ahead and show all its normal forces. So here, force of gravity would equal to the mass of the object, which is 40 times 9.8. We'll make this our normal force coming back up. Our normal force in this case would equal to 40 times 9.8 going back up. Again, we don't have to worry too much about the normal forces because this is a frictionless surface. So this one here would be the force that C1 is placing on 40, and we've already defined that as 26 newtons right here. And again, do this in different color. This is a force pair right here. Okay, and now we'll have the force that C2 is placing on the 40. What I'm doing on this one, I'm just letting this one here be C2. So now I'll go back to Newton's second law. The summation of forces in the x direction must equal to the mass of the object times the acceleration in the x direction. We will get minus 26 plus the force that cable 2 is placing on the 40 kilogram object must equal to the 40 kilogram object times the acceleration, which is 2. Oops, sorry about that. Make that into 2. We'll solve for that, move the 26 over, and we'll get the force that the cable 2 is making on the 40 object is going to equal to 66 newtons. Okay, and that's all we got to do there. Go ahead and circle a few of these things so we'll get mixed up in the crowd here. So that's 66 newtons, so we can come right back in here and we'll do this with green. 66 newtons. Now we want to find out what's taking place here. The easiest thing to do, and you got all kinds of objects here, or options. We can do a free body diagram of the 16. Last time I did a free body diagram of the cable. This time let's just do one of the 16. It works just as well. Both approaches will give you exactly the same answer. So I'll come down here, draw my dot to represent the center of the 16. So I have 16 times 9.8 coming down. I'll make that straighter, sorry about that. 16 times 9.8 coming down. Boy, let's do this again. 16 times 9.8 coming down. Move that up. I don't know what the problem is here. Normal going back up. Again, we got that mass. What did I say? 16. So we got 16 times 9.8. So we can say the force of gravity is equal to 16 times 9.8. My normal force must be the same. 16 times 9.8. Now I'll have this force going back here, and we don't know what that force is now. That's the force that C2 is placing on the 16 kilogram object, but we do know the force going to the right, and that force is 140 newtons. Again, Newton's second law, summation of forces in the x direction must equal to the mass of the object times the acceleration in the x direction. We got minus F that C2 is placing on the 16 kilogram object plus 140 must equal to 16, which is the mass of the object, times the acceleration, which is going to be 2. That gives us minus F C2 on the 16 is equal to, that's 32 minus 140. That gives us minus F C2 16 is equal to minus 108. So then we know that the force, that C2 on the 16, must equal to 108 newtons. And we come back to the picture and we'll go ahead and put that in there. Newtons. Okay, again, not too bad. All I'm doing is following Newton's second law, F equals ma, all the way through this problem. Great free body diagrams make all the difference in the world, and really this problem will just fall apart. All right, best of luck.